Okay, so we've already established that the negative work is equal to the change in potential energy, and work, of course, is the integral of force with respect to position. But if you have this expression, think about the integral as an antiderivative. This is saying, what is it you take the derivative of in order to get this quantity, the derivative of with respect to x? And you can see that it follows that if the integral of force with respect to x is the change in potential energy, then the derivative of the potential energy with respect to x is the force. Now what we're going to do is look at a graph of potential energy as a function of position, and of course in that graph the slope would be the derivative of the potential energy with respect to x, and the force then would be found by finding the derivatives here. But don't forget that negative. That force is not equal to the derivative, and they will tempt you with that mightily. It is equal to the negative of the derivative. And so the graph that you get looks like this. Notice here you have constant zero slope, and so you have constant zero force. Here in this region you have constant negative slope, so you have constant positive force. Here where you have a frown, that the slopes are decreasing, getting more and more negative. Here the force would be increasing, getting more and more positive. Here is a zero, so the slope is going extrema. The slope there is zero, and so the force is zero, but it's surrounded by a smile. The slopes are increasing, and so the forces would be decreasing, going from negative to positive, going from positive to negative, and so on throughout this graph. You have to convince yourself that we've got zeros, and that where the slope is positive, there the force is going to be negative. Now, you have a chance to do this on your worksheet with a different graph. You can do it now or later. The other thing we are going to do with this graph is to consider a situation where the total energy of our system is 5 joules, as indicated by this yellow line. The total energy is going to be made up of kinetic energy plus the potential energy. And if the total energy of the system is 5 joules, then what is the kinetic energy at x1? Well, the potential energy at x1 is 5, so the kinetic energy would be 0. And at x2, what would the kinetic energy be? Well, the potential energy there is 0, so the kinetic energy is 5. Here, where the potential energy is 3, the kinetic energy would be 2, and so on. This location in the graph right here is spoken of as a turning point. That if you have an object approaching that point, as its potential energy rises, its kinetic energy is getting less and less, that it is slowing down. When it reaches this point, it will stop. Its kinetic energy is 0. It cannot go beyond that point, because that would mean that it would have imaginary velocity, negative kinetic energy. So this is a point where it stops and turns around. We call it a turning point. Notice that when you are at that point, the slope is negative. That means the force is positive. That means the object is going to be accelerated in the positive direction. And so if it is there, it will be caused to move this way to larger and larger x values. And so it comes down the graph. Let's consider another situation where the energy is 1 joule. Well, suppose you were an object and you were trapped in here. That suppose you started right there. Well, the slope there is positive, so the force is going to be negative. That is, there's going to be a force in the negative x direction, an acceleration in the negative x direction. An object at this point would be accelerated back this way. And then, when it reaches this point, again, this is all the energy is potential, so the kinetic energy is 0. That's a turning point, and it's going to, again, because the slope is negative, the force there is positive. That is, it's going to push it back that way. And so it gets pushed back and forth to either side of this well. We say that this point here is a stable equilibrium. That it's in equilibrium because the net force is 0, right? Because the slope is 0. But if you go in the positive direction, you experience negative forces that push you back. If you go in the negative direction, you experience positive forces that push you back. And so there you have a stable equilibrium. If the total energy of the system is 1, we say that you are trapped in this well. You are trapped between those two turning points. If the total energy system was not 1, oh, wrong thing moving. Well, we just leave that green bar there. That this point here is also in equilibrium. The net force is 0. But notice, if you displace in the positive direction from that, you have negative slope, which means you have positive force, which means if you displace positively from that equilibrium point, the force, the acceleration, will cause you to move further away. If you displace negatively from this equilibrium point, the slopes there are positive, and so the force is negative. You will be pushed further in the negative direction. So this is an unstable equilibrium. You are in equilibrium, but any displacement from it causes you to move away from that point, as opposed to the stable equilibrium you had here. This region here, we would call it a neutral equilibrium. It is an equilibrium. The force is 0, but if you displace positively, the force is 0 still. You are neither pushed back nor away from the equilibrium point. So that is a neutral equilibrium. Okay, then on your worksheet you have the opportunity to work through all of those kinds of questions over again with the new set of data. Please do a good job with that. Okay, we have a checkpoint. Again, and please watch carefully. Oh, and it's cut off. This is an X here. Let's put it on there. This is an X. So it is again a potential energy versus position graph. And so the same sort of discussion we had before would apply. Please do A and B and put those results on your worksheet. Finally, a problem that it's just worth exposing you to so that you will have seen it before, and the next time you see it, you'll do better with it. That we have this box of tamales that is sliding along a frictionless floor, and then it hits a spring. And at that point, the box is now sliding on a floor that has friction. It causes a retarding force of 15 newtons on this box of tamales. And they want to know what the maximum compression of the spring would be. In this case, making a free body would be a big mistake. The force that you are getting, I mean, you could make a free body and indicate the forces, but to try to work from it would get you nowhere, because the forces are constantly changing with position. And if the force is changing, that is force from the spring, then you cannot have constant acceleration. And if you don't have constant acceleration, then all of those kinematics formulas you are so familiar with will not work. So what do you do in such a situation? And the answer is, don't do it in terms of kinematics, do it in terms of energy. I would like you to set up such a problem by starting by saying, I am doing this problem in terms of energy. You write energy equals energy, meaning energy is conserved. If you like, the energy at the beginning is the same as the energy at maximum compression. And then what sort of energy does it have at the beginning? Well, it had kinetic energy. What sort of energy does it have at the time of maximum compression? It's going to have energy stored in the spring, elastic potential, and there's going to be heat from that interaction with the friction. Please write this symbolically, and then beneath each of these put in the formulas that apply to them. Notice that for the heat, I'm looking at the force times the distance through which it acts. I'm looking at the amount of work done by friction to talk about how much energy was transformed into heat by friction. And then, of course, you could put in the values and finish the problem. I'm not so interested in that as setting up a problem to be done in terms of energy and showing your work. This is the level at which I want you to show your work. Here's another problem. This time, the tamales are sliding down onto the spring, and you have friction. Ask yourself what is different. Again, the force will not be constant, so you have to do this in terms of energy. But what new energy is present that wasn't present before? And it is gravitational energy. That this time the box was not sliding. It started off stationary, so it's not kinetic at the beginning, but gravitational potential. And again, it turns into elastic potential and heat. But please be very careful. You need to not take this 2 meters times the sine of 35 to get the distance the box has fallen. You need to also consider that when we're at maximum compression, the box will have gone down just a little bit further. That the total height is x plus 2 times the sine of 35. That's how much further it went down when you reach the point of maximum compression. Notice this is quite doable. You have that x, it's going to be a quadratic. You'll get 2 solutions, but it is a problem that you could do. Care is needed. This is the form in which to do such problems. Thank you and good night.